Now we're going to talk about some important theorems about these differential operators. The first one is Gauss theorem. And Gauss theorem states that if I take the volume integral d tau divergence of a vector v, this is equal to the closed surface integral d sigma dot v. So that's the surface that is going to be at the boundary of this volume. So that will be the defined by the boundaries of the volume over which we're taking this integral. So this is known as Gauss's theorem. And in order to show this, let's consider the integral definition of the divergence, which is written for a closed surface S surrounding the infinitesimal volume d tau. So we have to remember the integral definition of divergence, limit as S and V go to 0, closed surface integral d sigma dot v divided by integral volume integral d tau. So if we're considering for an infinitesimal volume d tau, a version of this integral definition, then we can write divergence of the vector v multiplied with d tau is going to be equal to the limit as S goes to 0 for a very small surface area, closed surface integral d sigma dot product with our vector v. Now let's consider this volume that is d tau 1 and then also the neighboring volume d tau 2. And they have a common surface in between them. And for this common surface, we can talk about two different d sigma vectors. D sigma 1 vector that will point in this direction, that's in the normal direction, outward direction of this volume. And d sigma 2 vector, which would be pointing into d tau 1 volume, because that's going to be in the outward direction for d tau 2. And if I consider the dot products d sigma dot v for these two, v dot d sigma 1 plus v dot d sigma 2 will be equal to 0. Why? Because d sigma 1 and d sigma 2 point in opposite directions, so these dot products, they are basically collinear but pointing in opposite directions. The dot products will add up to 0. The common surface contribution cancels out. So basically what I have done here is considering the right hand side of this equation, divergence of v d tau 1, I'm applying it to the volume d tau 1. And then I have added to it divergence of v for the volume d tau 2. This must be equal to the closed surface integral for the first volume d sigma dot v plus the closed surface integral for d tau 2 d sigma dot v, and the surrounding surface area is S2. So this is equal to S1 plus S2 d sigma dot v, but because the common surface contributions cancel out for this product, for a finite volume that consists of a sum of these volumes d tau 1, d tau 2, etc., instead of using this infinitesimal volumes, I can say that for S1 and S2, since the common surface cancels out, basically I can just consider the outer surfaces of this total volume, which is defined by d tau 1 and d tau 2, because the contribution from the common surface is 0. Therefore, we have the integral over a finite volume d tau divergence of V is equal to the closed surface integral d sigma dot V, where the surface is defining the boundaries of that finite volume. So this result is known as Gauss theorem, and it's basically based on the fact that for each differential volumes, neighboring differential volumes that I consider making up a finite volume, the common surfaces contribution cancel out in the integral of d sigma dot V because of the normal vectors pointing in opposite directions, and the dot products with the vector V will add up to 0. Okay, so the first important theorem we talked about was Gauss theorem, which states that the integral over the volume of divergence of B d tau, this is for a finite volume, this is equal to closed surface integral d sigma dot V, where S is the closed surface surrounding that volume. Now, using the integral definition of the divergence, we can write for a finite volume as V goes to 0, this is divergence of B d tau is limit S goes to 0, closed surface integral d sigma dot V. So for a very small differential volume that I take here, I consider divergence of B d tau 1. This is the closed surface integral S1 d sigma dot V for considering all of these surfaces. And for divergence of B d tau 2, I have to consider these surfaces. And there is a common surface here where the right-hand side of the equation tells me d sigma dot V terms, because d sigma 1 and d sigma 2 are pointing in opposite directions here, will add up to 0, so the common surface will give no contribution. Therefore, for a finite volume, which consists of integral divergence of B d tau, this is going to be the closed surface integral S d sigma dot V, where S is basically the boundary of this total volume that we're considering, total volume.